Hey guys, here we are, section 4.3. I'm going to break this section up into two smaller chunks. We're going to do increasing, decreasing in this video, and the next video will be about concavity. So just a refresher of what increasing and decreasing physically means on your graph. These should have arrows on them, right? And so this graph has a domain of all real numbers. So increasing simply means you are going up, you're increasing in the y-axis, in the y direction as you go from left to right in the x direction. So you're increasing up to here. This happens here at 1. Then you're decreasing afterwards till about 4. And then you start to increase again. Now in this case, you start to flatten out right at 8. And I'm going to claim that that actually is a horizontal tangent line. And so if there's a horizontal tangent line, that means your slope is 0. Which means for that one particular point, right, for this point right here, your tangent line is horizontal, which means you are not increasing or decreasing, and then you're increasing afterwards. And so the way we would write this out using interval notation, we're increasing from negative infinity to 1, and then union 4 to 8, but 8 here again is a horizontal tangent line, and so then after that, 8 to infinity, we're increasing also, but we're not increasing at 8, because at 8 you're neither going up nor down because your slope is 0, and if you have a slope of 0 you're flat, and if you're flat you're not going up, you're not going down, you're not doing either one. Alright, some books do it differently, but we do it that way. And then decreasing from 1 to 4, that's it. That's all it is. So if I do give you a graph like this to tell me increasing, decreasing, or concavity for that matter, remember that I'm not going to give you things that you have to guess at. It's going to be whole numbers. It's going to be nice values. It's not going to be, oh, well, that's a 1, but not really. It's a 0.95, haha, gotcha. I don't do that kind of stuff, right? So anyhow, all right, so let's look at the other type of problem that is going to be more prevalent, and that is when you're given a function in symbolic notation and we have to do the derivative in order to find it. So the step-by-step process is up top. Since step 1 is identifying the critical points, and critical points come from the derivative, I want to find the derivative. I'm going to do it by changing this to a 1/3 power so I can use my power rule, and then this is going to be a product, so we have to do the product rule. So the product rule says to take the derivative of the first times the second function as it is, plus the first function as it is times the derivative of the second function, bring down the 1/3. t minus 7, subtract 1 from the power. 1/3 minus 1 is negative 2/3. And then the derivative of the stuff inside, chain rule, the derivative of t minus 7 is just a 1. Remember guys, with these videos I will, other than breathing, I will go straight through them pretty much, and so if you need to pause or if you need to rewind, you always have that option. Okay? So what do we do now to find critical points? Critical points are when the derivative does not exist, or it equals 0. So we're going to try to get this equal to 0, and these are almost always going to be factorable. Something can be factored here. That doesn't mean multiply it all the way up. That means look for common factors. There's a t in common. There's also a t minus 7 in common, and so we're going to factor out a t minus 7, but the question here is, what power of t minus 7 do I pull out? Well, if you have x to the 5th minus x to the 3rd, okay, this has nothing to do with this problem, but it's how you factor. Then what do? You take the lower power of x, in this case x cubed, and you divide it out. And when you divide it out, you subtract the powers to see how many are left. So here's x to the 3rd factored out, and x to the 5th, you factor out an x to the 3rd, you're left with x squared. 5 minus 3 is 2. And then obviously when you factor the whole thing out, you're just left with a 1. So that's what we're going to do. We're going to factor out the lowest power. Negative 2/3 is lower than positive 1/3. But then when we do that, watch what happens. Okay, so we're left with a 2, and then t minus 7 was to the 1/3 power. How did we factor again? We divide, and so that means we subtract our powers. So we subtract the power. Well, the power is already negative, so we're going to subtract a negative 2/3. Okay? And then from here, we're going to be left with a t and a 1/3 because we took the whole power out front. Okay, so if we play around with this a little bit more, I'm going to rewrite the negative 2/3 power as a positive power in the denominator. Easier to work with that way. And then here, when you have negative negative, what does that do? That pluses the two together, and so I get 1/3 plus 2/3, which is 1. And so I just have 2 times t to the 7th to the first power plus 1/3 t. And then, of course, we can simplify the inside one more time. This is distribute the 2. 2t minus 14 plus 1/3. 2 1/3 is 7/3 t minus 14. So there's my final function, and it's set equal to 0. And so when I have a fraction equal to 0, like in front here, that means the top is equal to 0, and of course the bottom cannot be equal to 0. But again, critical numbers come from when the function, the derivative function equals 0 or does not exist. If the denominator were to equal 0, it would not exist, so we have to count that as a critical number. And then we need to solve this also for t. All right, so t equals 0 is obvious. This is equal to 0 or not equal to 0 when t is equal to 7. So I'm going to say not equal to, but this is still a critical number. And then if I solve this for t, add 14 to both sides, multiply both sides by 3/7, the reciprocal, I get t equals 6. So I have 3 critical numbers here for my first derivative. And so now I need to create a sign chart for that first derivative and evaluate different points on it. So I'm gonna take this function and rewrite it again over here on the next page instead of drawing that way too far. So bear with me for a second because you probably have it written down a little bit different. H prime of t is t over t minus 7 to the 2/3 times 7/3 t minus 14. I don't know why I'm talking like a sportscaster all of a sudden, but hey, there you go. So coming up around here, we're going to take a number line to make our sign chart. Ta-da! Label it H prime because that's what we're evaluating, and then put on there all of your critical numbers: 0, 6, and 7. Trying to make this as exciting as possible. Watching a video is not always that exciting, I know. So now pick numbers representative of each of these intervals. You can pick all sorts of different numbers, right? But you got to pick a number in each of this interval. And then what do you do with each of these numbers? I can't hear you. That's okay. And so it's h prime of -1. We plug in -1 for t everywhere. Remember, I don't really care about the sign, the value. I care about the sign. So even though I have a -1 over -1 minus 7 to the positive 2/3 times 7/3 -1 minus 14, even though I could figure out this, and if you need to figure it out on your calculator, that's great. It's easier if I just say, okay, this is negative. This is pretty clearly negative, a negative minus a minus more. And this guy, look at what we have here. This is a 2. Power of 2 means square. That means this is always going to be positive if it's not 0. So I have negative, positive, negative. 2 negatives give me a what? Give me a positive. If I plug in 1 to h prime plus 1, positive 1. Okay, same idea. 1 minus 7 to the 2/3. Plug it in here. 7/3, 1 minus 14. We get a positive, and here this is still negative. And so 1 negative is going to give us a negative sign. Okay, and then you're still going to plug in 6.5, and you're still going to plug in 8. When you do that, you're going to get numbers that are positive both times. Okay, so you can do arithmetic. I'm not going to keep going through that with you. And so what does that mean? That means your function has a positive slope, so it's going up. Then it has a negative slope, so it's going down. Then you have a positive slope, and then it must flatten out or something, and then you have more of a positive slope. So to answer the question, when am I increasing? That's exactly when my first derivative is positive. Remember this -1, I wrote it in blue for a reason. This is a test value. This does not have anything to do with your interval. Your interval is from negative infinity to 0. I also am positive from 6 to 7, but I leave out 7 and then 7 to infinity. Now, in a more advanced calculus setting, you may have to test what happens at 7. If 7, for example, was a vertical tangent line, if there was a vertical tangent line there, then technically you're increasing still. At that point, you never flatten out, you're going straight up. But we're not going to get into that technicality. So basically, if it's a critical value, you should leave it out of your endpoints for increasing, decreasing, or concavity for that matter. You're decreasing only in one interval from 0 to 6. This graph probably looks similar to the graph that we looked at the beginning, except something weird happens at 7 because the derivative doesn't exist there. Okay. So there are your increasing, decreasings. As far as local maxes and mins, what happens at 0? You go up and then you come back down. You have a peak there. So that means you're a relative maximum, right? And at 6, you bottom out here. You have a valley, so you go down and up. That's a relative minimum. All right, but then what do we say happens at 7? Well, as far as the first derivative is concerned, nothing. We go up, we flatten out, or we cusp or something weird, and then we go up again. So we don't change from up to down or down to up, increasing, decreasing, or vice versa, and so this is neither. This is not a local extremum. Okay? So that's how you do increasing, decreasing, concave up and down. Check out the rest of your 4.3 increasing, decreasing problems from your worksheet, and we'll take your questions on Monday. Thanks.